This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. In this video, I will be explaining the relativity of simultaneity. In the previous video, we discussed Galilean relativity and the postulates of special relativity. One postulate states that the laws of physics remain constant in all reference frames, meaning that there is no universal reference frame, and the other states that the speed of light remains constant in all reference frames. Because of light, Galilean transformations don't work. To fix this, take a spacetime graph in reference to the speed of light. The letter c represents this speed, which is 299,792,458 meters per second. On the graph, the world line of a particle of light will always form a 45-degree angle. We can fix the problem with Galilean transformations by tilting both the space and time axes so that light still forms a 45-degree angle. This can be thought of as rotating the graph in 3 directions instead of only one, explaining why it's okay to tilt both axes. To determine the tilt of Lorentz transformations, we can use the world line of an object that is at rest within that reference frame. That means that that reference frame can be called the object's rest frame. If the object starts at position 0, its world line will become the time axis, and then the space axis will tilt equally to preserve the speed of light. An interesting thing occurs on the graph when you place 2 simultaneous points on it. This means that they happen at the same time. When we observe the point from the other reference frame, we notice that those 2 points, called spacetime events, are no longer simultaneous. Conversely, when we look at it from a reference frame moving in the opposite direction, we notice a change in the order those events occur. Therefore, one cannot say with certainty whether or not 2 events occur at the same time, because simultaneity is relative to the observer. Spacetime is not absolute, and so the relative speeds at which objects move can determine whether or not 2 events seem to occur at the same time. Causality seems to be threatened by this, since the order of the events was able to change in different reference frames. If the order changed, then how can you determine which caused the other? The answer to this question will be explored in future videos. So as you can see, some crazy things occur just because the speed of light is constant. In future videos, we will explore why time is perceived differently beyond just the space-time graph, and we'll even discover how time travel really works. You see, classical physics is an excellent approximation on regular scales, but when you reach fast enough speed or large enough masses, you need relativity to explain events. Similarly, when you get too small, you require quantum physics to describe situations. This breakdown of classical physics will lead to even crazier things than just time travel, reframing your understanding of the entire universe. If you enjoyed this video, please give it a like. If you wish to further explore conceptual modern physics, subscribe to my channel and join me in the Physics Directive. Long live the Empire!